And what we have to do is we have to solve this system. Now, how do we solve this system? How can we possibly solve the first equation, for example? Well, the right-hand side is known, right? The left-hand side is unknown. So what we can do, we can integrate with respect to x. And this is what we never did before, but this is something we can easily do, right? We know how to do partial derivative. Now we have to do partial antiderivative. Right? So we consider the right-hand side as a function, but we only think of one variable x. And we treat y and z as constants. And then we integrate the right-hand side with respect to x. So as I integrate the first equation with respect to x, I'm supposed to get e on the left. Right? And the right-hand side, so let's do integration with respect to x. Integral of this is going to be 2/3 x cubed. Right? Integral of y squared with respect to x is going to be xy squared. Integral of that with respect to x, 3x z squared. Integral of that is going to be a half x squared y. Integral of this with respect to x is minus 3xyz. And integral of that with respect to x is x squared z. Alright? Plus a constant. Now, what should we say about the constant? It should be a function of y and z. It's just not a constant number. Right? If you were to do the calculus 1 antiderivative with respect to one variable, it would be just a number. Now we are doing partial antiderivative. So the statement here is that if instead of a constant we have any function of y and z, and if you take this right-hand side with that unknown function of y and z, and you take the partial derivative of that with respect to x, then that partial derivative will be exactly equal to this. Because that function of y and z will be differentiated to 0 with respect to x. Right? So that's the reason, and that's what you should not forget. That's the only difference between the calculus 1 antiderivative and the partial multivariable antiderivative. You have to keep track of the variables you leave in that constant. Okay, now, so that's so what do we see? Well, we see that we found actually the energy, the potential energy. We found the function. But not completely. We have a lot about this function and some unknown thing. Now the idea is that if we integrate the second equation, we will figure out some precise thing about the function, and there will be also some unknown thing left. And integrating the third equation will give us precise thing plus some unknown. Now the funny thing is that those precise things are going to be different. And the reason is that some terms are hidden in this unknown constant. So the idea now is that we integrate each individually, separately. And then we have those three equations. And those equations are about the same E on the left. E equals E equals E equals. Now what we will try to do is we will try to match all these three equations. And now my process of solving, starting with the second equation, is going to be that I'm trying to match the integral from the second equation to this formula. So let me look at the first. Well, let's integrate with respect to y. Right? We integrate the second equation with respect to y. The first term is going to be 3x squared y. Is there such a term there? 3x squared y. No, it's not there. So it's new one. I'll put it right there. 3x squared y. Now what about integral of y squared with respect to y. It's 1/3 of y cubed. Is there such a term here? No. So I'll put it on the side. Plus 1/3 of y cubed. What about integral of that with respect to y? It's minus 3yz squared. Is there such thing there? No. Minus 3yz squared. It's new stuff we are discovering about E. Integral of this with respect to y. It's 3/2 y squared z. No such thing yet. And the integral of this with respect to y is xyz. And there is xyz. All right. Okay. xyz. Okay. That's the integral of that with respect to y. Right? So I integrate all these terms, didn't I? Yes.
Is there a reason you put the x squared y under the constant? Because we have the negative 1/2 x squared y in the first.
Negative half. Oh no, there is no reason. I would like that to be actually here. And I would like that to be compared. So it's plus 3x squared y. Okay. Alright, so I accidentally ran into a randomization that I didn't want, but well, you see the answer here? It says none. Right? So sorry, I just overlooked, but I'll take the next randomization, and I'll use this one to show you how to solve this problem if it doesn't have a solution. Because there are two possibilities for you. And for WebAssign, those are kind of the same. For the test, those are going to be different. For the WebAssign, if you believe there is no solution, you just type none and you get your point. Right? For the test, I would like you to explain why you believe that there is none. Because none is very simple to try. You can spend your first try on none and get your free point without any solution, right? But I still wanted to explain why. Now let's see why. Why is it that in this case we don't have a solution? Yeah.
I have another question. Is there a reason why we don't have a constant function in terms of x and z?
Good question. The only reason is that I haven't finished writing the.
Oh, okay.
So my last question for you was: did I integrate all the terms?
Okay.
And then I went on tangential discussion. So yes, we have to add a constant, and that constant should be a constant with respect to x and z. Those two I didn't use as a variable for integration. Okay, now the second equation is complete. And now what we see is that those two equations say a very different thing about the function. One equation says it should have minus 3xyz. The second says it should have xyz. Right? So we pick such a place where two equations don't match. And then the thing we ask ourselves is the following. Is it possible that this term that doesn't match to this one is actually hidden in that constant? Is it? No, it's not. Because the constant can be only about x or about y and z, right? But the term we have is about x, y, and z. So basically the reason that we can never match is that this term cannot be hidden in the constant and it doesn't match what we see in that equation. And of course, this is not a rigorous description, rigorous statement of of a problem. Now we have to write down the rigorous explanation. Why is it that it is impossible to find the function? Here's the idea. The idea is that we look at these two terms and we compare the first two equations. Basically, the fact that we see mismatch of these two equations indicates that those two equations disagree. Right? Now, our job is to figure out what is it exactly that they disagree in. Right? To point out, well, they disagree here and here. So, how do we do that? The idea is that there are two ways. Okay. Well, the idea is that we can look at the first equation, which says partial of e with respect to x is equal to something. And we can differentiate that first equation with respect to y. All right. With respect to that variable. And I will also then later differentiate the second equation with respect to x. Okay? And my hope is that the contradiction throws up that these two things must be the same, because basically, given a function e, it doesn't matter which order you apply the partial derivatives. But since these two formulas disagree, I expect the right-hand sides to be different. So let's see what the right-hand sides are. I differentiate this equation with respect to y. So what's the partial of all that with respect to y? 0 here, 2y, 0, minus x, minus 3z, 0. And partial of this with respect to x is going to be 6x, 0, 0, 0, plus z. And now this is a contradiction. So the contradiction is not in the statement that, well, you can visually not match something here because some functions don't match. It's not like descriptive contradiction like that. It is very precise contradiction when assuming that a function exists, these two partial derivatives must be exactly the same, right? And the computations show that those two are not the same. Well, that's a really contradiction. Okay? And of course, for these examples, for this particular example, those are very much not the same, right? But basically, what we observed here, the mismatch of these two terms, can be traced down there, because derivative of this term with respect to x and y results in minus 3z, results right here, and derivative of that term with respect to x and y results in only z, which is there. So that mismatch resulted in obvious mismatch of the same things. And of course, the functions, well, the equations don't match in many different places. So that's why they are so different. But at least we were able to figure out one place where they're definitely different. Well, basically we used this mismatch as a hint of how to find the contradiction. We figure out that we have to compare first two equations. The way to compare them is to differentiate each of them with respect to the other variable, and then to compare the results. And those results will not be the same if you don't have those matching. That's the whole thing. So those must be the same. And this is contradiction.